density 2 is essentially an integer number model 2, so essentially it's just a binary, 0 or 1, or you can map it into -1 and 1, depends how you define it. But it just will have two values. So then, yeah, we have different possibilities for these operations, and this will give me this table. So we're talking yesterday about the time reversal symmetry, and the time reversal operator is an operator that transforms t into -t. It leaves x and change p to -p. And so I want to draw your attention to this formula here, because I think there was some confusion yesterday. Which, okay, so the thing that t change p to -p is that, it's this transformation. It's not that t over p is -p. So, okay, so this transformation with the t -1 on the other side, it will be -p. Okay, now from this, you set this transformation and this, and you use the commutator, you will get that t must transform in this way. So it has to be proportional to the conjugation. This is somehow clear because you see you have to change t to -t. And then you look at the Schrödinger equation, t is just in the derivative. So you have IH bar d dt. So in order to change t to -t, you have just to conjugate. So it has to be proportional to the complex conjugation operator. So in general, you can write it like, like this is a unitary transformation t, ut, followed by this complex conjugation. If you play a little bit with these identities here, you just will end up that t squared must be either 1 or -1. These are the only two possibilities. Now for bosons, so for spin integer particles, so you will have that t squared to 1. For spin 1/2 particles, it's squared to -1. For the case of so spin 1/2 particles, so you will have this form for t. So for boson, it's typically just k, just the complex conjugation. And if you have more dimensions, like in the value of the Young equation, in which the system is double because you have particle-like and Hall-like sectors, then you have also to apply this at each sector, so you have to take the tensor product with the 2x2 unit matrix, this tau note. Okay? So now I think if you, even for, you use this with p, so you just will get -p because, when you apply t over p, so the only thing that will change p is the conjugation. It just will change p to -p because p is minus IH bar, the gradient, so, okay? And so you will get, t over p just -p t. So you have this. So this will give you, then you have p, and you will get -I, and this will be -p, okay? And this is just -p tau, okay? So this now, p just will be -p tau -1, so this is just -p, okay? And you can find t squared for this case. It's just -I sigma y k minus I sigma y k. Now I sigma y, this is a real matrix because sigma y have the, so k is not doing anything because this is real. So this is just -I sigma y minus I sigma y, and then k over k squared is just 1, and then this will give you -1. Right? So -I times -I is -1, sigma y squared is 1. So 1, I mean the unit matrix, right? So we're talking about matrices here. Right? Okay. All right, so, yeah, so then, when you know what is your time reversal operator, so you just check whether it commutes or not with your matrix, and then you have 3 options. three possibilities. One is that it doesn't commute, then you don't have this symmetry. And you have another two possibilities, is that it commutes and t squared is equal 1, or it commutes and t squared is equal -1. Okay. So the other symmetry that we have is particle Hall symmetry. So this symmetry essentially, change, so make this the spectrum symmetric. So for each state that you have with energy E, it tells you that there is a solution, also a solution with energy minus E. So essentially, if you apply this operator to your wave function at a given energy, it just will give you the wave function at the minus this energy. Okay? So this is what the particle Hall or the charge conjugation does. So if then this charge conjugation commutes with the Hamiltonian, then you have particle Hall symmetry. If it doesn't commute, you don't have it. Typically, you have, in this Bagaglio-Dejean Hamiltonian, you will always have this particle Hall symmetry. Okay. Now, I must say that this is not it's an approximate symmetry. It's not an exact symmetry. So this Bagaglio-Dejean Hamiltonian, you get it after doing all this mean field approximation. So within this mean field approximation is an exact for the mean field symmetry. But if you have, in other situations in general, it's not. Okay. So then you can also write this operator as in this form. So it's a unitary transformation followed by the complex conjugation, and it can square to plus and minus 1. So the form it takes, it depends very much. It depends on your system. It depends on the basis you are using, the order of the basis. For example, if you have your Bagaglio-Dejean equation in this form, you can find that this complex charge conjugation operator will be of this form. This tau x is just the matrix, is the x Pauli matrix. I'm just calling tau and sigma, just tau for particle Hall space, sigma for spin space. Okay, but it's essentially this is just a tensor product of Pauli matrix sigma x with sigma naught. Okay, sigma naught is the identity matrix. Right. Okay, do you remember what this tensor product?
So tau x is the Pauli matrix.
Yes. Okay, so your BDG Hamiltonian, for example, is a 4x4 Hamiltonian. Okay, so you have your electron sector, you have let's say delta, delta whatever you have here, and here you have, let's put sigma naught here. Okay, sigma naught is just the identity matrix. It's just 1 0 0 1. Okay, and then you have here the whole sector. Okay, so this is whole sector, this is whole sector, but you have a spin in each of these sectors. So this is 2 by 2 because you have a spin here, you have a spin here. So the way you build the scenes typically with this tensor product of a matrix that acts on the particle Hall sector and a matrix that acts on the spin Hall sector. Okay, so let's say here for this operator I have tau x. Okay, I have this combination. So tau x is just the Pauli matrix. Okay, so it's just 0 1 1 0. Okay, and then you take it, and this is the unit matrix 1 0 0 1, and you see when you do this tensor product, so this matrix goes to here. So this is particle, this is Hall. This is a spin, this is a spin. When you do the tensor product, this matrix goes to this block. So a spin is put into the particle block, and this will put the spin into the Hall block, and so on. Okay, that is the idea of this notation. But mathematically, it's just it's just zeros and 1 0, the same like Pauli matrix. Okay. All right. So if you change the order of the basis, so this is you can use the order of the basis in this way, or you can change it. And then, of course, when you change the order of the basis, or you change your basis, your operators are going to change also, right? So what I want to say is that you have to be careful when you are calculating this or finding this operator, because it's tricky, you have to take into account what is your basis. If you are not sure, so then just try to prove this to see that it really works, okay? But I'm giving you for these canonical cases. For this canonical case, is just this form. If you change the basis, well, you just have to do is, you have to swipe, to swipe the order. So, and it is like a unitary transformation essentially that you will do, and then C will change according to your new order of the basis. Now, if similar what we have for the time reversal symmetry, if this charge conjugation operator anti-commute with the Hamiltonian, we have particle Hall symmetry. But if it does not anti-commute, then there is no such a symmetry. So we have, again, three possibilities, right? So we have possibility that it have the symmetry or it doesn't have it. But if it have it, I still have another two possibilities, which is that C is squared to 1 or C is squared to minus 1. So I have three chances, three possibilities for the time reverse. I have three possibilities for the particle Hall symmetry if I combine them. So this gives me 9 possibilities. And I still have another possibility, which is bringing by the this chiral, also known as sublattice symmetry. So, and this is the system we have this symmetry if the Hamiltonian anti-commutes with the chiral operator. So the chiral operator, you can essentially the chiral operator, you can build it like this. It's time, with the time reversal and the charge conjugation, and essentially transfer so that the time reversal, which change your wave function, let's say at k, will give you would map it into wave function at minus k. Charge conjugation match the wave function at energy E to the wave function at energy minus E. So chiral just will change because it's the two things. It will change your wave function at K and E to your wave function at minus K and minus E. Okay. So this operator you can show actually that that it always is squared to 1. There is no minus 1 for this operator. So it's square only to 1. So we have this other possibility, which is whether you have chiral symmetry or not. So from 9 plus 1, you have 10. So that is the 10 classes you have in that table. Okay, just coming from all these combinations. So so one interesting thing is that if you have both time reversal and particle Hall symmetry, then for sure you also have chiral symmetry. Okay, because if T commute with H and C anti-commute with H, you can prove that then H will anti-commute with H. Now, if you don't have, if you have, let's say, time reversal, but you don't have particle Hall, then you won't have chiral symmetry either. If you have particle Hall and you don't have time reversal, also you don't have chiral. But it may happen that you don't have particle Hall or you don't have time reversal, but you still have chiral symmetry. Okay? So, so combination of all of them give you these 10 classes that are here of all these situations. Okay, so now we know how to classify this. And so the point now is, well, we know the classification. So what is the topological invariant that will track me the behavior of my system? So, okay, so before we have, we have this discussion that we cannot go continuously from this normal band structure into the inverted one because, so I cannot go from S state to S state without closing the gap. So I cannot go from this situation to this situation without closing the gap. So in general, so when we have a Hamiltonian, it depends on any of these classes. It of course either have a gap or either it doesn't have a gap. So the gap is closed. So the question is, if I give you the symmetry class of this special and the number of dimensions along which you have translational invariance, so how many distinct gap phases, it could be insulator or superconducting, are there? So, and for this, when I mean, we have to distinguish with these distinct phases or not. So the phases may be equivalent if you can deform it. You can deform the band structure continuously into the other. If you cannot do that because you will need to close the gap, then they are not equivalent. Okay. So here are, it's an schematics of different situations you may have. So let's say I have a Hamiltonian that depends on many parameters, so this P1 up to Pn. And I made the phase diagram. So in the phase diagram, what I have is essentially independence of these parameters, whether my Hamiltonian have a gap or not. Okay. So the gray zone will be, let's say, for a Hamiltonian that doesn't have a gap. So let's say a metal. Okay. And this Y region is for a Hamiltonian that have a gap. Wherever you have some gray zone means that you don't have a gap, so you are closing a gap. So in this situation, let's say I can have my Hamiltonian which have a gap here, so all them, but I can then go smoothly from any point, by changing these parameters. As long as I'm not going out from this region, I know that my Hamiltonian is always gap. And so I can deform, of course, when you change the parameters, this band structure is going to deform, but if it's not going out from this region, it's always gap, okay? So here we have only one of these non-equivalent phase. But I could have something like that. So I can actually have that I will have two gap phases, but from going from one to the other, I cannot do it smoothly. Okay, so I have two phases, they have a gap, but I cannot go continuously from one to the other. This is this example here, okay? So here is gap, but there is no way I can go from here to here through continuous transformation without closing the gap. So this is this region here, right? So if I have to go from this, I have to, I have to go through this line here, which I put in gray because it's indicating that the gap is closing there. And then I will have a phase transition, a topological phase transition when the system crosses this, this X point. So I change the parameters, and when I change the parameters such that the system crosses this point, then I have a phase transition, and I go from B to A. There are two gap phases, but they are different, so they are non-equivalent. They will be described by different topological numbers. Okay. So this will be typically the case in which you will have this C2 topological invariant, because you will have then just two numbers, one describing this phase and one describing the other phase. Okay? But you may have a situation, you can actually have many of these transitions here. So then you will have more numbers, more integer numbers. So this will be the case of the Z topological invariant. All right? So when we calculate these invariants, of course, you can always just calculate, make the calculation with the Hamiltonian that you have and fight with this. But this is very convenient typically to flatten this Hamiltonian. So to make it smaller in a way, okay? So what is the idea of this flattening? So the idea is that instead of working with H, you will work with this new Hamiltonian. The flattened Hamiltonian is just H divided by the absolute value of H. Of course, H is an operator. So if I want to calculate this, I will need to use a spectral decomposition. So then I can write this new operator in this form, okay? So with En are the eigenstates of H, eigenenergies, and Psi n are the eigenstate of H. So if I assume, this essentially is just the sign of En, so I can rewrite this flattened Hamiltonian in this way. What is the advantage here? The advantage is that this, you look at the eigenvalues of H, they are going to be just plus or minus 1, okay? So you can also rewrite these Hamiltonians in terms of projectors. So, at zero temperature, your Fermi energy is the zero energy. So all the states below are occupied, all the states above are empty. So you can use a projector, this projector over the negative energies. This will give you the occupancy of, the trace of this projector will be the occupancy of this occupied states or the number of occupied states, and this will give you, because this is for the positive energy, so above Fermi energy, the trace of this operator will give you the number of empty states. So then you can write actually, this flattened Hamiltonian combination of these two states, or you can rewrite it in this form because the sum of these two p's must be equal 1, right, of these two projections, because psi n is complete, it's a complete basis. So then the trace of H will give you this difference, the difference between empty and occupied states. If the system have charge or particle Hall symmetry, this will be 0 because the spectrum is symmetric, but so the trace is not necessarily 0 in the general case. Anyway, so there are nice properties of this new flattened Hamiltonian. Again, so the eigenvalues are just plus minus 1. You will get as many plus 1s as positive energy state you have, and as many minus 1 as negative energy states you have. Then it is unitary, and it's also squared to 1. So the thing is, that the thing that allows you actually to work with this flattened Hamiltonian instead of the real Hamiltonian is that they have the same properties. They have the same topological properties. So you can work with H, but if you work with the flattened one, it is simpler, okay? And it have the same topological properties. So the idea is more or less in here. So if this is your spectrum, okay? So let's say you have all these bands, and in that case you have a gap, Fermi energy is here. Essentially, when you flatten the Hamiltonian, what you are doing is mapping this spectrum into this spectrum in which you have just minus 1, 1 for the values of the eigenvalues, okay? So all these bands will, positive energy bands will map to 1, all negative energy bands will map to minus 1. Now, if you have a gap, so then, so if you have a gap, it always will look like that. So you will also have, if you have a gap in this, you will have also a gap in the flattened Hamiltonian. If you don't have a gap, like in that case, you will also have a gap. So you actually will have a singularity because it's H over absolute value of H. When H goes to 0, or the energy goes to 0, you have like 0 over 0, which is not well defined. So you will have these singularities in there. So it means you really can map this topological structure of the topological property of the band structure of your Hamiltonian into this flattened Hamiltonian, which is then easier to calculate. Yes?
So then if your spectrum doesn't have a gap, you cannot map to that. You cannot map to.
If it doesn't have, yes, it just will make a jump. Yeah, I don't know what is this topological number is not well defined when the gap closes. It is just only well defined when you have a gap. Okay. So when the gap closes, you will see just a discontinuity in this. Just let's say it's like going from integer to integer, right? So you go from 0 to 1. You cannot go continuously. So at the point that you have this transition, what you will see is a jump. So there is no integer between 0 and 1, so it's not defined. Okay. All right. So okay. So we have now my Hamiltonian. Then I can. So there is another property that I can use for the case of this that you have chiral symmetry. So you can actually show that if you have chiral symmetry, so your Hamiltonian commute with this chiral operator, and so you can again use H, or you can use the flattened one. So I will be using the flattened. So it can show that if your flattened Hamiltonian commute with the chiral operator, so I think this is an error here. It should be anti-commute, by the way. It's so you have this is anti-commutation here. I will correct this later on, but just have it in mind. Then, so you can actually block anti-diagonalize this Hamiltonian. Okay. So if H and S anti-commute, then for sure there is a unitary transformation that can transform H into this form. So anti-diagonal. So the diagonals are 0, and you have matrices only like that. Okay? So let me just switch here for a moment. I won't go through all these details, but I have some notes about this. And here there is a demonstration of how you can do that. Okay, so I will post this so you can have a look at this at home. Okay, so, and then this Q matrix, this Q functions or matrices depends on the dimension of your Hamiltonian. So, fulfill these conditions. So they are, if they are matrices, they are unitary. So you see all this structure that you have at the beginning, after all this transformation, if you have chiral symmetry, simplifies the lower sim, because instead of having your Hamiltonian, which have many elements, you flatten it and then you transform it and then just get this simpler form. So all this is 0, all this is 0. So everything is just, all the information is just in this Q, okay? Now, so I will show you now an example of how to calculate things with this. And this is so I will try to go more or less in details with this example. And this is perhaps the simplest example we can have for this. Is the so-called Such-Riefer-Higger model, or SSH. And it's a model that was introduced to model this polymer change of polyethylene. And essentially, it's just modeling this chain in this form. So we have some cells, and we have hoppings, so inter-cell hoppings, and we have also intra-cell hoppings. So the Hamiltonian that you describe, and in all these situations, we always put the Fermi energy is the 0 of the energy. Okay? So the Hamiltonian, then we have this structure here. So we can have this, hopping from A to B inside the same cells, or we can have hopping from A to B, but from different cells. So N actually mark here the cell. Between, let's say, you cannot see this. Okay, let me just. So you can have, N is essentially the cell. You can have hoppings between A and B. These are here. Or you can have hopping from A and B, but from different cells. From N to the N plus 1 cell, let's say, here, okay? So I will assume that this B and W is larger than 0 or equal to 0. So they are real and equal or larger than 0, just for simplicity. You can consider more general cases you want, but let's keep it like that for simplicity. So I have this Hamiltonian, and now what I want to do is to look at the topological properties. Now, if I look at this chain with this Hamiltonian, it's a finite chain, right? It's an open chain. So I have a beginning, I have an end. First size is n equal 1, last size n equal capital N, okay? I cannot easily calculate this topological invariance. I need time, translational invariance. So I need to make this periodic in order to work. And again, so remember the idea here is that you have a finite system, but you make it periodic, and then you calculate the topology of this bulk of this periodic system, and this will give you information about what will happen if this periodic system is not periodic anymore. What happened at the edges. So I need to know what is the bulk. I don't care about edges. I make it infinite. No, and I look at the bulk. And this topological number at the bulk will tell me whether I will have edge states or if I make the system finite. That is the trick. Okay, so I need to make it periodic. So I make it periodic. So if I make it periodic, then I have a good quantum number. Momentum is a good quantum number. So I can make a Fourier transform. This is Fourier transform of my functions from the position space into the K space. I use this boundary condition, so just matching the ends of the chain. Essentially, it's like just closing the chain, that there is no beginning and end anymore. Okay. So if you can put this, substitute this in the original Hamiltonian, this is what you will get. And then if you want to write the matrix of this, so you just compute the matrix elements. and these are the matrix elements, and then you will get this Hamiltonian 0, because when you have this A and B, so the diagonal terms goes to 0, and then I end up with this matrix here. This is the matrix of my Hamiltonian in K space, of this translational invariant Hamiltonian in K space. This is a very nice model because you see, we are already on this form. For this specific case, you don't even need to do any transformation. You are just for free in there. It's not always the case. So in many cases, you will have to do transformation to get to this, okay? But here, this model is simple, and so the basis that give you this is straightforward, but sometimes it's not like that. Okay, so I have now my Hamiltonian, and I want to see whether my Hamiltonian have a gap or not, and where the gap closes or not. So if I look at the eigen energies of this Hamiltonian, you can solve it analytically. So it just, H, the determinant of H minus E equals 0, you will get these two possible values for the eigen energies, plus minus absolute value of Q. So the gap will close if these energies are 0, right? So, and this energy is going to be 0 if Q of X is 0. So if for some Q, if for some K, Q goes to 0, then it indicates that my gap is closing. So I will have here a topological invariant, which is this C number, which is the winding number. So I will go into the details about the winding number in a moment, but before, as an exercise, let's see what is the symmetry, what is the symmetry class of this Hamiltonian, okay? So we can use the time reversal operator. There is no spin in this Hamiltonian, so it's spinless, so it just will be then the complex conjugation, the time reversal. So now I told you that this small detail here, okay? So in position space, I told you that that this will give you the time reversal symmetry, okay? Now what happens when you are not in position space, but you are in K space? So you can write this like this. Or like this also. Okay, so now when you are in K space, it's going to be something different. So you will have actually this, and I will explain you why. Okay, so why I have this minus K? Well, because T have a conjugation, okay? So the conjugation change P to minus P. But K is a real number, so if I change P to minus P, okay? And so since there is translational invariance, so I can just substitute P with H bar K, right? Now, what is the point? So when I do the conjugation over P, it will change P by minus P, but if I do conjugation over K, the conjugation is not changing so I have to force it to change the same of K, okay? So you either put P, you can do this, you can just put P everywhere, so you will have this, and after that you change P to H bar K, okay? Because, this will change P to minus P, and then you substitute P by H bar K, and then you will get minus K, right? But if you are working just with K, then you have to do like that, okay? That is the thing here. All right, so then we have this, I think there is time reversal symmetry in this system which is spinless, and the time reversal operator is squared to 1. You can also check that in principle, actually, there is no charge conjugation in this, because there is no particle hole in the system. However, you can create a sort of fake. So I mean, fake is that it's physically have not this meaning of particle hole symmetry, but mathematically it acts like if it works, okay? So, and this in that case will be the sigma c k, or sigma c the time reversal operator. And you can check actually that this actually anti-commute with the Hamiltonian. So, and again, so this, probably this is not very, I should write this like here, because there is a minus k here, so the actual thing is this. I will change this, so just copy and paste, but and then change to k, but so for the case of the chiral symmetry, this is for the time reversal symmetry in k space, and for the chiral symmetry will be for the particle symmetry will be this. So you will have minus h minus k. So here is plus, sorry. Here is plus. Okay. So this is position space. This is k space. So this is k space. And in position space, you have this. Okay. All right, so all in all, so you have, again, you don't have the charge conjugation, but you can put the charge conjugation. And then with, so you have, you have charge conjugation and you have time reversal, then you will have also chiral. So you can build the chiral operator that way, and you will find also that it's commute with the, well, this is again, is in this meaning also. I think I need to correct these equations. Anyway, so you have the three symmetries, and all of the operators squared to 1. If you go to the table, you will see this is BD1 class. Okay, so we can quickly go to the table here. You can see here BD1, so have the three symmetries and all the operators squared to 1. And if I am in a 1D, which is this case, it's just a chain, then I will have this C invariant, okay, which is in that case the winding number. So any question before entering the winding number? So if you want to do this, real in the physical meaning, so it won't be in BD1 because it doesn't really have this physical particle hole symmetry. So it don't have real particle hole symmetry, and also don't have real chiral symmetry because it's coming from this. And then you will end up just with time reversal symmetry, so it just will send you back to the A3 group, okay, and class. Okay, but I want to illustrate the C invariant, so I'm imposing this fake symmetry so that we can illustrate it, okay? Mathematically, it works. It's just a physical interpretation that you give, okay? But it just will tell you mathematically, it will tell you what happened to this Hamiltonian. Now, you may think, oh, is this really a particle hole symmetry or is not? Or okay. Anyway, so we have a C invariant. This C invariant is the winding number in this case. And what is the winding number? So the winding number is essentially, if you go to a closed curve around a point, it just tells you how many times you go around it. So, and by convention, it is positive if you go counterclockwise. If negative, you go clockwise. Okay, it's essentially like what I have here. So you see, I'm going through this, if I'm going through this closed curve, I will go twice around this point here in the middle. Right? Is this clear or not? So if you are not sure, just look at this line here. Okay? It just give you a couple of turns, okay, around it. So this is the winding number. And of course, it's an integer because, well, if it's a closed loop, you have to go an integer numbers of around. Okay. Okay, so there are some remarks here. So again, I just remember that if the system is gap, then Q is going to be different from 0 for all K. Okay, because the energy will be 0 when Q is 0. Yes.
I have a question. Usually, what like this curve, what represents this curve in the system?
I will show you. This is the what is the curve. Okay, so okay, I will show you what is the curve, but for now, this is the concept of widening number. So you may ask, widening number of what? What is the thing that is widening? I will show you in a moment. Okay. Okay, so again, since the energy is just given by the absolute value of Q, so it's going to be gap as long as Q is different from 0 for all K. So Q is this function here. So okay, this function here, that's what we calculated from this matrix element for the Hamiltonian. This is Q. Oops. And this is the thing that is going to be looping here. So this is a complex function, okay, because you have, so if you look at this Q on this complex plane, it's going to give you a closed loop. Why? Well, because K goes from minus pi over A to pi over A, the Brillouin zone, and they match. So it just will make your function. If you change K from minus pi over A to pi over A, and you make a plot of this function, I will show you how this looks like in a moment, but you will see that this is actually a closed loop. Okay, and then what you will what you will be looking is how many times this closed loop goes around Q equals 0, which is when you have a gap. Okay. Now, what is the important point here? Is suppose you have a loop, so with a given specific, let's say, winding number. So the only way you can change the winding number by by continuous deformation of the curve is if you go through the center, if this. Okay, so here is the simplest case I can have. Okay, so let's say my point is here, my loop is here. What is the winding number? The winding number is 0, right? So I have winding number is 0. If I want to change the winding number, how I can change it from 0 to some other value? I have no option that crossing this point, okay? And that is the important thing here. So I will have to make the formation so that I cross it and then go into the other side, okay? Then I change from 0 to 1 when I cross it. So crossing, if it is in the, if I put Q in the complex plane, crossing is Q equals 0, is my origin of coordinates. It just tells me whether when I look at this curve, it tells me whether it goes to 0 or not. And Q equals 0 is exactly when this gap closes. So the number is telling me, when I change the number, it's telling me whether I cross this point or not, so whether the gap is closing or not. Okay, so that is the idea. So you consider this continuous deformation of the Hamiltonian while preserving the gap, and this corresponds this continuous transformation of this Q of X complex plane curve. And if for some point this is 0, Q is 0, then you know that the gap is closing there. So the conclusion here is that this winding number is constant under any gap deformation. So as long as you keep the gap, so there is no closing of the gap, then your winding number is constant, it's not changing. If when the gap closes, so it goes through Q equals 0, then you change the winding number, okay? So the winding number is only, can only change when you have this transition through Q equals 0 when the gap closes. And for this specific case, because it's relatively simple, so you can, yes?
Can we tell that by changing the hopping parameters that when the gap is closing and when it is not, so that we can have a case diagram?
Yes, that is the idea. So I have this, I have two parameters in this model, right? So V and W, so they, right, so that's exactly the idea. So I will now tune these parameters and see whether, I have a topological phase transition or not, okay? Whether I'm all the time with the same winding number or I change my winding number. Now, this specific case is relatively simple. So typically, you have to calculate this winding number, right? So you, and it's an integral of some logarithm and so on. In the notes, there is some explanation about that. But in this case, we don't even need to calculate it, so, because you can visually see what it is. Okay, that is the nice things of this model. So, okay, where is the matrix element? Okay, we have this matrix element. So this is Q, but this is V plus E, I, K, A, W, okay? So in many books, you will find just K. I put just K. K is, A is just the lattice constant. So this is dimensionless. In the books, you may find just K because you just say, okay, K is dimensionless. Okay. All right, so this is my function. This is real. This is real, so I can divide this into real part and imaginary part. So the imaginary part, the real part of Q depends on K, of course, and the imaginary part of Q also depends on K. And now K is changing from minus pi over A to pi over A, which is the Brillouin zone, okay? And then, so I just build this in my complex plane. So for a given K, I look what is the imaginary part and the real part. I change K to another value. I look and I join all these points and get my curve, okay? So how does this curve look like? Well, it actually depends, okay? So we have this curve here. Let's say if we have, so it looks like this, okay? So like what we have here in the, oops. No, like here, okay? So you see now if, it's essentially this curve is just a circle with radius, the radius of the circle is given by this parameter, and the distance from the center of this circle to the y-axis is given by this v parameter. So v is just this distance, and when you plot this imaginary part and real part, this is what you get, this circle there. Okay. Now you see, if w is smaller than v, so the radius is smaller than the distance to the origin, then the winding number is going to be 0 because the circle is, the center is here, the circle, so winding number is 0. So I'm in a trivial phase in that case. Yes?
Is V equal to the winding number? No, V is
No. The winding number is, so this is this Greek letter nu, which happened to look pretty similar to V, but okay, it's not the same. Okay. So these V and W, these are these hopping parameters. Nu is the winding number. These here are winding numbers, okay? And these here are these parameters, okay? So they actually look pretty similar, but yeah, they are not the same. Anyway, so you see in that case you have nu is equal to 0, so you have a gap phase, right? Trivial in that case, but you can, if you increase W at some point, when your radius W is equal to V, then you cross this point. You cross Q equals 0. meaning you are crossing the gap, okay? You continuous increasing V and W, so the radius becomes larger, so you change your winding number from 0 to 1. So at W equal V, you will have topological phase transition from this trivial state at nu equals 0 to this with nu equal 1, okay? So how does it look like if you look at the spectrum of this translational invariant chain? So here is the spectrum. So this energy is a function of K. So and nu equals 0. So essentially, you are in this, this is very small here, like a point essentially here, nu equals 0. You get this gap phase. You start to increase W, but still keeping it smaller than V, so you still have a gap. When W is equal V, then you have this topological transition, so the gap closes. You see that it's closing here at the ends, okay? Then it reopens when you have W larger than V. And again, so you go to this. Now you will say, well, yeah, they look exactly pretty much the same. What is the sin? How is this that I'm calling trivial different from this that I call topological? If I look at this, well, the difference is they have different winding number. And since they have different winding number, if you put edges, so this is again for the bulk, this is an infinite system. If you put edges, you will see the difference, okay? So if you look at the bulk, this one, you made the system infinite. So the only thing I can tell you is they have different topological numbers. You won't see this difference in the spectrum. So you will see the difference in the spectrum when you put the edges, okay? And
this is actually occurring because of the preservation of time reversal symmetry and chiral symmetry.
Sorry?
These topological phases are robust because of the protection of chiral symmetry and time reversal symmetry.
Well, in this case, yes. In that case, they have the three symmetry. Okay, so this is the topological phase diagram. So just essentially V versus W, because if W is smaller than B, you are trivial. W larger than B, you are topological. So it's just essentially this line here, V equal W, which is the line corresponding to the topological phase transition. Below you have trivial, above you have topological phase. Now, what happened if now I go back to the real change? So not this that I made infinite, but the one that is finite. Now I will see the differences in the spectrum, okay? So, but I can, we can figure out what we expect to see just from the model, okay? So let's go to these very extreme cases, okay? So let's go to this, this is the original model. But let's go to these extreme cases. So let's say W is 0 and B is different from 0.
We can have a break, or you can finish and then we can take a small break.
Okay, so let me finish this slide and then we have a break. So let's say that I have this. So I'm putting W equals 0. It means there are not these hoppings. These are the ones that correspond to W, right? And the intercells are given by B. So if I put W to 0, it means I don't have these intercell hoppings. So which phase I will have? Is what it is. It's going to be a gap phase. It's going to be an insulator. There is no way for conducting here, right? Because all this is broken here. So I will have, if I made the band structure in that case, I should get a pretty good gap at the Fermi energy. There is nothing to conduct there, okay? Now, and this actually corresponds to this trivial case. So because I put W equals 0, I'm always going to be, W is going to be always smaller than B, okay? But then let's go to the other situation, which B is equal 0. And then this will be the topological case, because then W is always going to be larger than B. But you see, if I put B equals 0, Then, so I still have this state here, so, okay? But you see, I start to get, I still will have an insulating phase because, there is no conduction, so you see, I cannot go from one end chain to the other, so it's gonna be still an insulated chain. But I see that I have these isolated states at the end of the chain. So this state, because there is no hopping to go here, cannot go everywhere. This state, there is no hopping, so it cannot go anywhere, right? So they are isolated here. So it means I will have this localized state at the end of the, and what's gonna be the energy of this state? It has to be zero, because if you look at the Hamiltonian, there is no on-site energy in this Hamiltonian, okay? So this is the Hamiltonian. There is no on-site energy. There is nothing with NA or NB. So meaning in this Hamiltonian, the on-site energies are zero. So these states that are going to be localized here, they must have zero energy. And this is what you see in the spectrum, actually. So, at B equals 0, you see these states with zero energy. At W equals 0, you have a gap. And, let's say you fix W to 1 and you make the plot of B, you see that you are going from this topological phase into the trivial phase, or from the trivial to the topological phase if you tune the other parameter. Okay. So, again, to finish this part, so if you look at this, you don't see the difference. The only difference you see is that the winding number is different. But this is enough. It tells you that when you put the edges, it's going to be different. And it's going to be different. And in the topological phase, you will have these zero energy states in the gap. Otherwise, you will have a gap. Okay. All right, so let's finish for this part. All right. And let's take a few minutes.